Today we will look at an example of the Galerkin method. So the Galerkin method is a method of approximating solutions of functional equations. So on one hand it is useful in numerical analysis because you produce approximate solutions of equations which you want to solve. On the theoretical side it is also a useful tool because by producing approximate solutions and showing that they converge in some suitable topology to the solution of a problem. So you prove thereby the existence of solutions of a problem. So we will illustrate the latter in an example here. Okay, so let omega contained in Rn, you have a bounded open set and gamma will be denoted will denote d omega. So let V be the space h10 of omega whole square with the product norm. And for u equals u1 u2, v equals v1 v2, uv in h1 in capital V, define a of uv equals integral on omega sigma I equals 1 to 2 ui vi dx plus integral on omega grad u2 dot grad u1 v1 dx minus integral on omega grad u1 dot grad v2 dx. Okay, so Cauchy-Schwarz inequality. So clearly by Cauchy-Schwarz inequality AUV is continuous. But look at AVV. So that will be equal to integral on omega sigma I equals 1 to 2 mod u vi square, and then grad u2 grad v2 grad v1 minus grad v1 grad v2, that will cancel, and therefore this is not V elliptic because we cannot express the L2 norm greater than or equal to the H1 norm. That is not possible. Okay, so therefore this is not an elliptic thing. So by the normal course of things you cannot use the Lax-Milgram lemma. So but nevertheless we want to find V such that AUV equals FV for every V in V, where Fv equals sigma integral on omega I equals 1 to 2 Fi Vi dx. So F equals F1 F2 in L2 of omega. So we will use the Galerkin, so we will try to prove the existence of a solution to the system of equations. So you have a system of equations because you are dealing in a product space, you have two unknowns u1 and u2 to find, and therefore you have two equations for them which are coupled because u1 and u2 get mixed up in the equations, and therefore you want to solve this and try to prove the existence solution. As I said, Lax-Milgram lemma is not directly available and therefore we want to show this. So H10, so V equal to H10 of omega square is a separable Hilbert space. Therefore, let us assume that V1, E1, E2, EM, etc. is an orthonormal basis for V. So the Galerkin method, so let us say Vm equals span of E1 to Em. So, the Galerkin method has the following stages. So, step 1, there exists unique solution um in Vm such that A of v equals Fv for every v in Vm. Okay. So, Fv is equal to sigma integral I equals 1 to 2 Fi Vi dx. Okay. Step 2, show that norm is less than or equal to C for all m. Okay, so this is a method of a priori estimates. And then thirdly, so we are in a Hilbert space, you have a bounded sequence, so there exists a umk such that umk converges to u weakly in V, and then show u solution of original problem. So, this is where we will have to use the properties of the bilinear form, linear form, etc., all these things. So, let us go and execute this program. Okay, so step 1, Vm is finite dimensional, implies all norms are equivalent. So, if you put norm m, V on m is equal to sigma I equals square 1 to 2 integral mod Vi square dx on omega. This is a norm, this is the L2 product norm, and this is also a norm which is equivalent to the original norm. So, A of is now Vm elliptic, we already saw that, saw it here, and therefore, and it is continuous, implies there exists a unique in Vm such that v equals Fv for every v in Vm. So, the first step is, actually you do not even need to show this, need to use this Lax-Milgram lemma. So, this is by Lax-Milgram lemma. If you write out this equation, you have to write it out for each basis function. So, I will just give you an aliter. So, you want to solve v equals Fv for every v in Vm. So, this is linear in V, therefore, it is enough to check for the basis element. So, this is Ei equals Fvi for every I 1 less than or equal to I less than or equal to m, Ei, sorry. Okay. Now, itself is a member of the vector space, so this can be written as some alpha j Ej mj, let us say alpha mj Ej, j equals 1 to m, and therefore, if you substitute it here, you get A of will be sigma j equals 1 to m Ej Ei alpha mj equals f of Ei, 1 less than or equal to I less than or equal to m. So, now you have m linear equations in m unknowns, namely alpha m1 to alpha m. These are the unknowns, and if you know these, if you can find these, then you can find and that solves the equation. So, you have a linear equation. So, you have of the form A alpha equal to f, alpha is this vector, and therefore, f is the column vector which is FE1 to FEM. So, that is known to you. And then A is the matrix Aij, and Aij is A of Ej Ei, and now using the L2 ellipticity and the of the bilinear form A, it comes that A is symmetric, is positive definite. Okay. So, A is positive definite, and therefore, every positive definite matrix is invertible, and therefore, there exists a unique alpha vector, and therefore, you have the solution UM. So, this is on the way of looking at the first step. Okay. So, now let us look at step 2. Step 2 is to find an estimate for the solution. So, you put V equals UM2 comma minus UM1, where UM equals UM1 UM2. So, if you do that, then the L2 part disappears. If you look at A, you have here the L2 part will disappear, these two will add up now. So, you will have grad UM2 square plus grad UM1 square. So, you will get that mod UM1 square 1 omega plus mod UM2 square 1 omega will be equal to integral on omega F1 UM2 minus F2 UM1 dx, which is less than or equal to mod F1 0 omega mod UM2 0 omega plus mod F2 0 omega mod UM1 0 omega. And you can say by the Poincare inequality, you have that all this can be less than C times mod UM1 1 omega plus mod UM 2 1 omega. And of course, you have A plus B whole square is less than or equal to A square plus B square. Now, 2AB is less than A square plus B square. So, this is 2 times A square plus B square, and therefore, you have that mod UM1 1 omega plus mod UM2 1 omega whole square is less than or equal to 1/2 of this, which is less than, so that is less than C by 2 mod UM1 1 omega plus mod UM2 1 omega. So, from this you get that mod UM1 1 omega plus mod UM2 1 omega is less than or equal to C, some constant C, different constant, but does not matter. Okay, so this shows that the step 2 is satisfied now. So, all the solutions are uniformly bounded. So, now step 3. So, UM bounded in V implies there exists weakly convergent subsequence. Okay. So, let us take UMK weakly converges to U in V. Okay. Now, V is a Hilbert space. So, if you look at, so any element V in V, V can be written as mod norm V square is equal to you have that the V equal to sigma j equals 1 to infinity V Ej Ej. Okay. And what does this mean? This means that is if you write Vm equals sigma j equals 1 to m v ej, then Vm converges to V in V. Okay, so this is the what you have. So now you have A of umk Vmk equals F Vmk. So now I want to pass to the limit. Now umk converges to U weakly, Vmk converges to V in norm, and therefore in fact you have, so what do you have, that A of umk Vmk minus AUV. This is equal to A of umk V plus Vmk minus V plus A of umk minus UV. Okay. Now the first term mod AU of umk Vmk minus V is less than some m times mod norm umk norm Vmk minus V. Now this is bounded because it is a weakly convergent subsequence, and this goes to 0 as we know, and therefore this goes to 0. Similarly, if you have A of umk minus uv, now this is a continuous bilinear form, so action on V gives you a continuous linear functional, and since you have weak convergence, this goes to 0 since umk weakly converges to U, and therefore you have A of umk Vmk goes to AUV. I have just repeated the fact that if you have in a by continuous bilinear form in a Hilbert space, then you have one weak convergence, one norm convergence, then the limit will be the correct one which you expect, and therefore this implies that AUV equal, this one of course converges to FV because Vmk converges to V, therefore AUV equals FV for every V in V, and therefore you have a solution to this problem. So remark, solution is unique. So if you had two solutions U and W, say U, W, two solutions. So you have A of U minus W V equal to 0 for every V in V, and now you put V equal to U minus W. So then you will get that mod U1 minus W1 square 0 omega plus mod U2 minus W2 0 omega equal to 0, and that implies that U1 equals W1 and U2 equals W2, and therefore the solution is unique. Okay. Now we also have, by the Relic-Kondrasov theorem, you have that umk converges to U in L2 omega square in norm. Okay. Now given any subsequence umk of any subsequence of there exists a further subsequence umk L which converges weakly to U, weakly, U solution of system. Therefore, what does it mean? So every sequence has every subsequence has a further subsequence, and the limit is always the same, and therefore you have that umk um itself converges to U in L2 of omega in norm. The entire sequence. Okay, so whenever you have a subsequence which always has a further subsequence and the limit is independent of the subsequence, then you know that the entire sequence converges, and therefore um converges to u in L2 omega. So now let us interpret the differential the equation as a boundary value problem. So u solution belongs to V. So this implies that u1 equal to u2 equal to 0 on gamma. So this is the boundary condition which is built into the vector space. Okay. So now if you take V in h10 of omega and you take V as V0 or 0V, okay. So then you will get that integral on omega of grad u2 grad V dx dot plus integral omega u1v dx equals integral omega f1v, and the other equation will give you minus integral omega grad u1 dot grad V dx plus integral on omega u2v dx equals integral omega f2v dx. Okay. So if we then you have that from this we can derive easily what is, take V is in d omega. So you get minus Laplacian u2 plus u1 equals f1, Laplacian u1 plus u2 equals f2 in omega, and you have u1 equals u2 equal to 0 on gamma. So this is the coupled system of linear PDEs which we have solved using this method of Galerkin, and in fact this has applications to the solution of the Schrodinger equation, which is important in quantum mechanics and so on. We will see that later on. Okay, so this is an example of the Galerkin method which is very useful in both. You can use the approximants suitably. In fact, the finite element method, if you are familiar, is a particular case of the Galerkin method. Here we have used orthonormal basis and used the first span of the first m vectors as the finite dimensional space. The Galerkin method, the finite element method, has a different way of constructing the finite dimensional spaces. So that is the only difference, and which exploits the powers of modern computers. Okay, so that is the importance of the Galerkin method.